So 200 years ago, people were already creating electric carriages. The first one in the United Kingdom was in 1839, which was designed by Robert Anderson up in Scotland. I couldn't find a picture of either of those vehicles, so you'll have to do with a picture of Wood's Phantom from 1902. But all these vehicles were electric. They had a battery to store energy and motors to make them drive forwards. So very similar to our cars, electric cars today. Interestingly, the peak in the last century of electric car production was back in 1912. And by 1928, all electric car production had ended for two reasons. It was due to cost and range. So the electric cars cost more, and people were concerned about how far they could go on a single charge. Now that's interesting, because that's the same problem we have today. Nothing's changed in the 90 years or so since then. And that's something we have to work on. And part of the adoption over the next 10 years is going to be really addressing those key things about the purchase cost of a vehicle and the range of that vehicle. Now, when we look at what industries think is going to happen to the automotive sector, what we see is not a simple energy source, one energy source for all vehicles. Different vehicles on our roads have different requirements, and we'll find that there's likely to be a mixture of different energy sources being used in different vehicles for different applications. So at the moment, you find that most cars are petrol, gasoline cars, and that we use diesel for some cars and trucks and so on. Now, there's an overall expansion there over the next 30 or 40 years in the number of vehicles on the road. That's a trend that's happening and will continue to happen. They're seeing about 30% of those being all electric, and we're certainly seeing that in government policy, looking at trying to make sure that the majority of cars are going to be electric by 2030 or 2035 for newly purchased cars. There's also a prediction there that a lot of cars will be hydrogen, so that's interesting, and that some will be hybrid, where you need range and you don't have the infrastructure to support that. So what's interesting is all the vehicles have some electric technology on them. Now, those of you who know the University of Nottingham know that we are heavily involved in electric vehicle technology and demonstrating electric vehicle technology. And one of the things that I've been doing over the last 5 or 6 years is running a superbike race team. So we built an electric motorbike, built a number of electric motorbikes capable of speeds of over 300 kilometers an hour, and we went racing on those bikes. So this is not a slow motorbike. This is a bike that can go around a racetrack faster than a BMW superbike. Now, there's a number of reasons why we did this. One of the reasons was to promote electric vehicle technology. So as a university, we felt we had a responsibility to demonstrate that the technology was good and exciting. There's nothing like a race bike to show that it's exciting technology. We could have put that same technology into a truck and driven it around campus, but it doesn't generate the same excitement. And we also wanted to push the boundaries of the technology. The great thing about going racing rather than producing a production vehicle is that we were able to try out and test new technology. And various PhD students have found electric motors, power electronic converters, and so on that they've designed have been put on that bike and taken out on the racetrack. It's been great fun for us because we've won a few things over the years. So in 2015 and 16, we were the European Track Series champions. In fact, in 2016, we were running 2 bikes and had great fun doing that. But the bikes themselves are actually designed around the Isle of Man TT. Those of you who don't know where the Isle of Man is, it's a small island in the Irish Sea between the island of Ireland and England. And every year they close some of the roads on the island for 2 weeks and race motorbikes around that track. Now that track is small local roads, and it takes about 20 minutes to drive around there at speeds of about 120 miles an hour average. So it's an exciting place to go and race motorbikes. Very hard place to go and race motorbikes, and gets lots of good publicity. You may recognize the gentleman on the right hand side photos there, who's our future King of England, and he was there. He's also an avid motorbike fan, it turns out. So we built a bike and we've gone and tested it by racing it against companies like Honda on the Isle of Man. And when you look at the drivetrain, the electrical part of that system, you find it's very simple. We have a battery, which is a large battery, weighs about 100 kilograms. That energy goes into a motor drive that controls the motor, and that motor drives a chain which drives the rear wheel of the bike. You'll notice there's no gearbox, anything like that on this bike. It's a simple, straightforward drive system where the motor drives a single chain, so you have a single gear driving the back wheel. Now, very nice, simple system, but there's a lot of technology goes into the various parts of that system. There's a lot of technology recently changing in the world of power electronics, so the controller to control the motor. And any of you who are electrical or electronic engineers will recognize some of those circuit diagrams there, showing the type of power electronic converters that we're using in those applications. And the new materials that we're using there have an important impact. What we're seeing is that the efficiency of the systems is increasing. Now that's important. So we've got the new materials in power electronics allowing us to increase the efficiency of the controllers in these electric vehicle applications. That's important because the weight of the battery depends on the amount of energy you need to store, and you would like that energy that you store in that battery to go into the wheels of the vehicle and not be lost as heat. So improving the efficiency of the system, we're also doing the same with the electric motors, is a great way to improve the overall efficiency and energy use of the vehicle. So the electric motorbike is just one example of the types of systems we can design, build and test. And we've used that as an example of a road vehicle. We've also been on a journey with electric aircraft, looking at, is it possible to get rid of jet fuel, something that's burnt relatively high up in the atmosphere, and something that is a significant contributor to the CO2 emissions and so on. So can we reduce or even eliminate what comes from the aviation industry, and can we do that again using electric energy? Well, we've been on a long journey with this one. So we didn't start with making the propulsion system of an aircraft electric. Where we started was making the aeroplane itself as a big system more electric. And when we looked at a typical aircraft 25 or 30 years ago, we found they had 4 power systems on that aircraft. One was electrical, which was doing important things like the in-flight entertainment, the lighting and the avionics. There's also a pneumatic system, which is a high pressure air system, which was used for the air conditioning, cabin pressurization, and ice protection. There's a hydraulic system used for the flight controls, and a bit of fuel pumping and oil pumping on the engine to get the jet engine to work. And the idea of the more electric aircraft was to go from 4 power systems to 1 power system to make the aircraft a little bit lighter and a little bit more efficient. And if you fly on modern aircraft today, such as the Boeing 787, you'll find that you won't notice it necessarily, but those aircraft have these more electrical systems and are therefore more fuel efficient. So we've been taking some steps in that direction for a long time. The next thing we want to do is to look at that 2050 goal, so 30 years time. This chart makes the assumption of a doubling in flights over a 50-year period from the year 2000. Even with COVID, this is probably going to happen. COVID causes a dip in demand, but previous experience of disruption to the aviation industry suggests it bounces back fairly quickly. And we see that if we took no action, we would double the amount of emissions from aircraft over that time. But we already have some known technology shown in the yellow area there, which is helping us to reduce the emissions from the aircraft. But there's a lot of new technology needed, which is the green area on that chart, if we're going to reduce the CO2 emissions by 50% whilst doubling the number of aircraft in the air. So a lot of work to be done and a lot of things we can do in universities to help develop this technology. And one of the things they're wanting to do, this is the roadmap from NASA, but there's plenty of others around, is to make the propulsion of aircraft electric rather than using gas turbines to provide the propulsion itself. And you can see that over the next 30 or 40 years, the idea of slowly larger and larger aircraft having propulsion systems, I'll say what I mean by a propulsion system in a moment, that are run electrically. It will then be another 20 years before those aircraft all get into service and displace the existing aircraft. So this is not a quick thing to do. This is something that's going to take many decades of work. But when we do this, we'll find that that will be something that will really help us to meet those emission targets for the aviation industry. And one of the things we find with this is that when we go into this electrification, we need some big electric motors that are high power but very small. And one of the things we're finding at the university at the moment, if you look at the chart in the top left there, is that the aircraft requirements for larger and larger electric drive systems has a particular trajectory, but the drives that we're able to produce at the university are well ahead of that curve. So that's the series of motors you can see built up on the left-hand side there. And those are just examples from Nottingham. Plenty of other universities are working in the area.
Sorry, Professor Pat, you have 2 minutes to end this presentation.
Yeah, that's okay, we'll be there. So it's important that when we look at this, we don't just think of the aircraft as being electric drive using batteries. If these aircraft are going to go for long distances, then we're going to need a source of electrical energy. So the chart on the right-hand side there shows a typical hybrid propulsion system, type of system we'll be using on aircraft until we get to the point in time when batteries are able to store enough energy. So the advantage of that is that the generator will sit in line with the passengers, generating electricity, and then we'll be using electric motors on the wing as the propulsion system. The reason we want to do that is because you can run the generator at its optimum point in terms of efficiency all the time, and because the motors are smaller and generally lighter than the generators, so present less wind resistance to the aircraft. So that's the sort of direction that we're going in with the aviation industry, and there's lots of technology going into that, lots of university research in various areas, materials, electrical, mechanical engineering, and lots of demonstrators. This particular demonstrator is a 4 megawatt demonstrator for a regional aircraft. And as a university, we've also got involved in some projects where we're actually looking at the integration of this technology onto aircraft engines. So this is one we've done with Safran Power in France, where we've put a motor and some power electronics around a traditional turboprop engine in this case, to provide a boost to that engine. Again, it's all about saving energy. It's all about the flight being more efficient and using less fuel. So hopefully just about on time. COVID-19 is going to cause a blip in demand, particularly in the aviation industry. We're seeing that. But a 2-year blip in demand is not significant in terms of the 30 to 40 year roadmaps we're seeing, particularly for aviation. And it has given an appetite for change. So that's something we'll see in the automotive industry. So the electrification of transportation is happening. Technology development is essential to that. And so therefore, any of you who are going into any relevant technologies as research in universities, you find that that's a great area to be in. Power electronics and electrical machines are key technologies that need to be understood as this industry changes. And energy storage systems really must improve if we're going to have the uptake of transportation electrification that we would all like to see for the good of the environment. So thank you very much for listening. I hope I've just about managed to do that in 20 minutes. And I will hand back to the chairman.
Thank you. Thank you, Professor Pat Wheeler, for the amazing, insightful presentation. Due to time limit, we have summarized all questions from the audience into one big questions here. So as we know, the transition from fossil fuel vehicles to electric vehicles will take times in some geographic region, especially in Indonesia. So what do you think is the key success of this transition, and how soon could electric vehicles be massively implemented in Indonesia?
Well, that's an interesting question. You can start implementing electric vehicles. Well, I suspect there's some already being sold. There's two things you need to do. One is to make sure that you have the vehicles on sale in the country. Right. And certainly in the UK now, I can go into most car garages and buy an electric vehicle. And I can walk down the road from where I live near Nottingham and buy an electric motorbike. So you need to be able to purchase them. But the other thing you really do need is the infrastructure to support them. Yes. If I buy an electric vehicle and I drive to the University of Nottingham, I can plug it in every day and charge it up. We have charging stations on campus. But when I drive a long distance, I also need to be able to charge up my car at service stations and so on the motorway networks. So, and there's constant complaints in the UK that there aren't enough charging points, that there's too many electric cars already on our roads for the number of charging points. So there's a need for that customer-facing interface to charge the vehicles. Now, there's also an ever-increasing demand to charge vehicles quickly. And if you buy a more expensive electric vehicle, you can almost fully charge it in about 20 minutes. But that puts a demand on the electrical system because you have to be able to get the electrical energy to that vehicle. You can do part of that with local storage, but part of that has to be the electrical network infrastructure, the electrical utility infrastructure to actually provide that electrical energy. And ultimately, as the number of electric vehicles increases, you're going to need to generate more electricity. And that puts a pressure on the electrical network operators to have generators coming from renewable sources. You don't want to burn oil and coal to create energy to put into nice clean cars on the road. That doesn't, it does actually make a little bit of sense, but that's not ideal. What you're looking to do is to incorporate renewable energy sources, solar, wind, or wave, whatever type of energy it is that's most abundant in a particular area, and to integrate that into the electrical network so that you can support all these electric vehicles and actually manage to charge them. So being able to make them and buy them, make them and sell them, buy them is important, but the infrastructure to support them, to me, is also important, because otherwise you end up with very frustrated customers.
Thank you so much for the answer. So we hope the infrastructure and also the demand of the electric vehicles would be increased rapidly in the future. And the future is also, we know it's now, so we don't have to wait for the future. So thank you very much for the presentation, Professor Pat Wheeler. And please have a round of applause to Professor Pat. And I think we come back to you, to our MC for today, Amanda and Dava. Thank you very much.
Thank you very much.